Hello, and welcome to the first video of the FP3 chapter, Further Coordinate Systems. On the screen, we're going to do a quick review of conics as an introduction to this chapter. So conics is a word you might hear to describe these four things. We've got circles, if you take a cross-section that is parallel to the base of the cone. But if you adjust your angle slightly, you'll get yourself an ellipse. And if you adjust your angle more so that your cross-section is parallel to the edge of the cone, so the center of this here is parallel to this direction here, then you have a parabola. And if you go a step further and you keep increasing that angle, you get a hyperbola. And of course, if you keep going, you end up parallel to the vertical in the cone, and then on the other side, you go back through these four. You have hyperbolas, parabolas when you're parallel to this side, and then an ellipse and back to the circle. So these four things are considered conics because you can get them from cross-section of a cone, as long as you cut at the correct angle. And you should recognize two of these, I hope. You've done this one way back, started that at GCSE, and you looked at that in one of the pure modules. And you've done this one in one of the pure modules, and FP1, I think. So those two should be very familiar to you. You should know the equations of those. Ellipse, I hope you've heard the word before, but you might not be familiar with the equation. And hyperbola, same, you might have heard of it. So these are the two we're going to look at in this chapter of the book. An overview of that, we're going to look at ellipses first, their equations, how to find their tangents and normals. Then we'll do the same for hyperbolas. Then we'll look at eccentricities, foci and directrices, and finish off with the problem-solving section on loci. This is a little bit different to the textbook. The textbook orders it slightly different. They introduce the equations of ellipses, and then they jump to this, and then they introduce this, and then they go back and look at the tangents and normals later. I prefer to group them together because tangents and normals are something you're familiar with other equations, so I think it should be fairly straightforward in terms of the concepts for you to do. So I've grouped those together. To begin, we're going to compare the equations of ellipses with your familiar equations for circles. You know the Cartesian equation of a circle is this. You've been using this since GCSE. Parametric equations, I hope you're familiar with these. If you take the radius and you do r cosine theta, where theta is this angle anti-clockwise from the x-axis, you get the x-coordinate, and if you do r sine of this angle, you get the y-coordinate. Ellipses are very similar, except obviously we don't have a fixed radius. This here, A, you can see in my diagram, is slightly longer. This is the major axis. B is slightly shorter, the minor axis. So as you move around, we don't have this fixed R all the way around. It changes. So we can't have a fixed R here. But we can do this. X squared divided by a squared plus y squared divided by b squared equals 1. This is the standard form for the Cartesian equation of an ellipse. And you can see that this ties in with the circle, because if a is equal to b, i.e. if you do have a circle, then you can call that anything you like, whether it's a or b or r, and multiply everything by it, and you get back to this equation here. So this is a specific type of ellipse, where a is equal to b. And the parametric equations are almost exactly the same, except r here becomes a, the value of the intersection of the x-axis, and y is equal to b sine theta, where b the value of the intersection on the y-axis. But you've got to be a little bit careful here, because this theta is not the same as this theta in terms of the angle on the diagram. You can see this theta relates very clearly with the angle here in the diagram, from the center point to the point you're looking at. But it is not this angle here, as it might seem to be. What it's connecting to actually is the circle that would be there of radius A, that gives that same x value. So it's this angle here. And you can see the x value of this point and the point that was there is the same. And this is called the eccentric angle. I'll just quickly finish this idea off. If you take B now here, the inner circle, and to get the same y value as the original point on the ellipse, you have to take b sine theta of this circle here, and you can see that that's the same theta because of the similarity in the circles. So this theta and this theta are the same as each other, but just be aware it's not the theta that you might expect to see on the diagram. So unlike the circle, don't go drawing thetas on your elliptical diagrams, because it won't match the theta that we use in the equation. And just again, this is called the eccentric angle. Now, I'll be honest, you could do the whole module without knowing that, but if you didn't know that, you might be tempted to draw the angle incorrectly on the diagram. Okay, we'll start off with some very simple examples, just using the equation here. We need to sketch E, where E is the ellipse with this equation. So normally I would recommend to put it into the Cartesian form. So we've got 4x squared plus 9y squared is equal to 36. For an ellipse, we always want a 1 on the right hand side, so divide everything by 36. We get x squared over 9 plus y squared over 4. And of course, you can connect this now with a 3 squared and a 2 squared, which tells you A is equal to 3 and B is equal to 2. And once you know those two values, sketching the ellipse is very simple. A is under the x, that's on the x-axis, so we've got a minus 3 and a 3. B on the y, 2 and minus 2. And once you've got your intercepts in place, just try to make an ellipse as best you can. And there's your sketch. Part B, write down its parametric equations. This is just as easy once you know A and B. You're simply writing down x is equal to A, 3 cosine theta, y is equal to B, 2 sine theta. And again, just a quick note, don't draw theta on your diagram because it won't correspond to this theta here. Question 2 is going to come up on the screen. Let me get rid of this. The ellipse E has parametric equations this. Determine its Cartesian equation. Well, they're already telling us from the parametric equations that A is equal to 3, B is equal to 5, so just put that into the form you know. 3 squared is 9. 5 squared is 25. There we go. As with all other functions you've ever done in maths, we can apply differentiation to find the gradient function, and once you've found the gradient at a certain point, you can then determine the equation of the tangent, or using m1, m2 equals minus 1, you can find the equation of the normal. And we can do the same thing here with an ellipse. It's just a new equation to work with. So find the equation of the tangent to the ellipse with the equation this at the point this. So what we need is to differentiate our equation to find the gradient, put in the coordinates of the point that we want, find out what that gradient actually is, and then put it into the straight line equation. Differentiating this, you can do it in two ways. On this first question, I'll do both ways to show that they give you the same answer. So we can do implicit differentiation. So we get 2x over 9 plus 2y over 4, and in order to differentiate y I need to times that by dy by dx for the chain rule, and don't forget the derivative of a constant is 0. So rearranging this I get dy by dx is equal to minus 2x over 9 times 4 over 2y minus 4x over 9y, and then evaluating that at the point given, I just substitute 3 cos theta and on the bottom 2 sine theta. So that cancels with that to give me 3, that cancels with that to give me 2, so we get a 2 on top and a 3 on the bottom. And that is the gradient at the point given. Now the alternative method is to use parametric differentiation. We know that this is x and this is y in parametric form. So if I do dy by d theta, I'm differentiating 2 sine theta, which gives me 2 cosine theta. If I do dx by d theta, I'm differentiating 3 cosine theta, which gives me minus 3 sine theta. And then using the chain rule, we know that dy by dx is equal to dy by d theta divided by dx by d theta. And that gives me 2 cosine theta divided by minus 3 sine theta, and you can see that that's the same answer. So whichever method you prefer, sometimes one will be easier than the other, but often it will just be your preference. Go for it. Once we know the gradient, we're finding the tangent, so we don't need to apply m1, m2 equals minus 1. We just take this equal to our m and use the equation of a straight line. Put everything that we know in, and that will be our answer. So y1 is 2 sine theta, m at this point is 2 cosine theta over 3 sine theta, and x1 is 3 cosine theta. And you could rearrange and simplify this, but if you're not asked to put it into a certain form, why bother? Here is the equation of the tangent to this ellipse at this point. A more general equation here. Show that the equation of the normal to the ellipse with the general equation this, at the general point this, is this long horrible thing here. So we need to do basically the same thing. We need to differentiate, and in this case I'm going to go straight into parametric differentiation. So this is our x again, this is our y, dy by dx is equal to b cosine theta. Sorry, dy by d theta, dx by d theta is equal to minus a sine theta. So dy by dx, the thing we want, is dy by d theta, b cosine theta, divided by minus a sine theta. But because we're doing the normal here, what we want is minus 1 divided by this. So the gradient for my equation is actually a sine theta over b cosine theta, because it's the normal, not the tangent. And then we put that into our equation, y minus y1 is equal to mx minus x1, and we get y minus b sine theta is equal to a sine theta over b cosine theta times x a cosine theta. And then to get what they want us to get, we just need to rearrange this. So we get by cosine theta minus b squared cos theta sine theta, just by getting rid of that fraction. A sine theta, let's expand this as well, get xa sine theta minus a squared sine theta cos theta. So I've multiplied everything by this to get rid of the fraction, and I've also expanded this bracket here. And then if we take this onto the right hand side and factorize sine theta cosine theta, then we're pretty much there. Just to make that explicit, I'll put this middle step in. And then we just need to factorize. Make it look exactly as they want it to look for your final line. And there we go. This is a result that you could memorize and use, but I wouldn't recommend memorizing it. It's big enough that you're going to have enough trouble memorizing it that you might as well just go through the process in the exam. Because if you need it in this form, then it might be asking you to prove it, in which case you can't just use it without proof. You need to prove it as I've done here. And if you don't need it in this form, but you actually need numbers, then I would suggest it's probably just as easy to go through this process with the numbers rather than memorizing this and then putting in the numbers. Here we have an example with some numbers then. We're trying to find the normal, but first we're going to find the value of theta. So we've got the point P this. It lies on the ellipse with parametric equations this. So we know x and y at point P. To find theta, just substitute these in to these equations. So if x is 2, then 2 must equal 4 cosine theta. So cosine of theta must equal half, so the inverse cosine of a half is equal to theta. And if memory serves, that is equal to either 60 or 300. Now we have two options there. So we're going to do the other one as well and see which one it is. So the y value at P is 3 root 3 over 2. And that substituted into the equation for y is equal to 3 sine theta. 3 disappears. Inverse sine of root 3 over 2. And that is equal to 60 or 120. So the angle that we need, the one that agrees with both, is 60 degrees, or in radians if you prefer. Now the reason we've got a second answer for both that disagrees connects back with the diagram here. Remember, this isn't actually the angle, but it gives an idea of what's going on. We've got one angle here that gives you the x-coordinate, but there's another angle in the same ellipse that gives you the same x-coordinate, even though it's technically not the angle in the ellipse. So we're getting two different angles here giving us the correct x-coordinate. And of course the same thing happens with the y over here. This one and this one will both give you the same y-coordinate, which is why you've got two angles giving you the y-coordinate here, and why that is different to the second angle on the x, and yet they share one, which is the one that we want. So that's why that has happened. That's why you need to do both of these in order to find the correct angle and be confident that it is the correct angle. Part B, find the equation of the normal to the ellipse at point P. So we need to differentiate. In this case we don't have the Cartesian form, so obviously it would be more work to put it into the Cartesian form to do implicit differentiation. So parametric differentiation is the obvious choice here. So dy by d theta is equal to 3 cosine theta, dx by d theta minus 4 sine theta. Therefore dy by dx is equal to minus 3 cos theta over 4 sine theta. And we know that cos sine theta is a half from our work here, and we know sine theta is root 3 over 2, so I could substitute those in now as well. So we've got minus 3 times a half over 4 times root 3 over 2. And simplifying that a little bit, the 2's cancel out. So we get minus 3 over 4 root 3. Normally I would rationalize that denominator, but we're finding the normal, so we're about to flip this fraction upside down anyway. Because the normal, I need to do minus 1 divided by this. So the gradient of the normal is 4 root 3 over 3. Put that into our standard line equation. With the things that we know. Y minus 3 root 3 over 2 is equal to 4 root 3 over 3 x minus 2. And that is the equation of the normal to the ellipse at point P. Okay, another general result here, and I would suggest that this one actually is worth remembering. So I'm going to go through the proof, but I would suggest you remember this result when it comes to your exam. It can be very useful. So the question, show that the condition for any general line to be a tangent to the general ellipse this is this. So if you've got an ellipse given to you, and you've got a line given to you, and you want to know whether or not it is a tangent, all you need to do is see whether or not this is true. If this is true, then this line is a tangent to this. If it's not, then it isn't. So to prove this is quite a bit of algebra, so we're just going to have to wade right in. What we're going to do is we're going to substitute the equation here for y into the y here, because obviously a tangent and an ellipse must meet at some point. So we get x squared over a squared plus mx plus c all squared over b squared equals 1. Now if I rearrange this by multiplying by a squared and b squared, we get b squared x squared plus a squared, and let me square this as well, m squared x squared plus 2cmx plus c squared, and all of that must equal a squared b squared. Expanding out this and collecting like terms, we get b squared x squared plus a squared m squared x squared plus 2a squared cmx plus a squared c squared minus a squared b squared must equal 0. Now this is just a quadratic equation, so let me tidy this up. We get b squared plus a squared m squared lots of x squared plus 2a squared cm lots of x plus a squared c squared minus a squared b squared for our constant. Now, thinking back to what we're trying to do, we're trying to show that this is a tangent. So when I substitute this in here, there must be a solution. They must touch, but there must only be one solution. They must touch only at one point. So when we put this into our lovely b squared minus 4ac in the square root, that must equal 0, so that there is only one solution, one point of contact, which is what makes it a tangent. So I'm going to substitute b and a and c, realizing of course that the ABC here are different ABCs here. I hope that's obvious. So substituting that in, we get 2a squared cm squared, and that's the b squared from the pink formula, minus 4 times a in the pink formula, which is b squared plus a squared m squared from our quadratic, times c in the pink formula, which is a squared c squared minus a squared b squared in our quadratic. And all of that has to equal 0 if this is going to be tangential. one point, one solution. So now I just need to rearrange this, and hopefully what comes out of all of this is this result. So we get 4a to the 4 c squared m squared minus, so we're going to have a squared b squared c squared times minus 4, so we've got minus 4a squared b squared c squared, and then we're going to have minus a squared b to the 4 times minus 4, so that's plus 4a squared b to the 4. Then we've got a to the 4 c squared m squared times minus 4, so minus 4a to the 4 c squared m squared, and then the final term, a to the 4 b squared m squared times minus 4, and a minus there. So we've got plus 4a to the 4 b squared m squared, and all of that still has to equal 0. Now fortunately, we can straight away say that cancels with that, and then we can factorize 4a squared b squared from each of these three remaining terms. And that leaves us from this term here, a b squared, from this term here, a minus c squared, and from this term here, an a squared m squared. And all of that has to equal 0, but we know that a and b can't be 0 if this is going to be an ellipse. So this non-zero thing here we can divide by this. So this thing here must equal 0. And that gets us the result that we need. If this is going to be a tangent. So there's two results in there. We looked at this one here, and we've looked at this one here. There's a third result for the tangent rather than the normal, and that is this one here, which we haven't proven, but you can go through the process. It's a little bit easier than this one. It's very similar. What I would recommend, although you can quote these without proof, is not to remember this one or this one, but I would recommend remembering this one here. It's a more useful result to remember. It's harder to prove if you're going to go through the proof. It takes quite a long time, and it's easier to remember because it's quite short. So I think this one's worth remembering for your exam. Now, because we've done two things in the textbook here, we've done the equations of ellipses and we've also done tangents and normals, you can practice all of these ideas using questions from exercise 2a for ellipses in general, and for 2D specifically tangents and normals. And maybe I'll see you in the next video for hyperbola.